This is Nanoscape. I'm Seth Zimmerman.
And I'm Erin Spain.
On this show, we venture into the frontier of nanotechnology
With experts in the field who are turning the science of small into the next industrial revolution.
This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University.
In science fiction stories, robots, they move like us. They're soft, responsive machines that can safely interact with people. But most real robots being used today are still rigid mechanical systems built for precision and control.
One familiar example from science fiction is Disney's Baymax, that inflatable healthcare robot from the movie Big Hero 6. Baymax is designed with a big soft body that can interact with people without hurting them. That's a great concept for a movie and a robot, but building something like that turns out to be as much a nanotechnology and materials challenge as it is a robotics challenge.
Our guest today is Ryan Truby, and he's working on that problem by designing robots from the inside out, where performance and intelligence emerge from materials engineered across scale, from the nano level up to the size of the machines you see today.
Ryan is the June and Donald Brewer Junior Professor and Assistant Professor of Materials Science and Engineering and Assistant Professor of Mechanical Engineering at Northwestern University. He also leads the Robotics Matter Lab, where his group develops these soft materials, artificial muscles, and bio-inspired sensing approaches that help robots move and behave more like living systems.
Today, we're doing what we're calling a cyberpunk reality check, but without the dystopian future, and finding out more about what it actually takes to build robots that are soft, capable, and safe by design. I don't know if cyberpunk really is the best terminology to use. Maybe it's cyberpunk adjacent.
Ryan will have to let us know. Ryan, welcome to the show.
Thank you guys so much for having me. I'm really excited to be here. Cyberpunk is not a bad adjective to continue with.
All right. Well, we're thinking about this future of robotics. I mean, we automatically think of these advances in artificial intelligence and better software, but you're looking to advance robots by rethinking their bodies instead. What made you start thinking this way?
Yeah, so that's a long career, almost lifelong kind of story. I started as a biomedical engineer in my training. I'm not a material scientist by training at all, nor am I a roboticist. I had the amazing opportunity to go to the University of Texas at Austin and study biomedical engineering, where I was just fascinated by the human body and how it works. I really was super fortunate to get involved with research when I was in my very early time at UT and started designing nanoparticle contrast agents to hopefully go out and seek cancer. And at some point, as you're designing these therapies, these like nanoscale robots, as people were like afraid we were making, you started to think about some of the material challenges of making something that's small, trying to scale all of these different materials to different relevant human technologies, but also just a deep fascination with how the body actually works. So that's where this all started happening of how do you build like biology? How do you assemble as biology does? And I really lucked out in terms of getting to do a PhD in material science and engineering. Ended up doing that PhD at Harvard University and really just started getting addicted to this kind of future of can we take inspiration from biology and starting to make materials that perform, move, sense, perceive, do things like we and other living organisms can do.
When you look at most robots today, they're super precise machines, but very stiff and mechanical. So what are the fundamental limits of that rigid body when robots leave the controlled environments and enter the real world?
Truly, this is what feels like the great barrier to what we're experiencing and seeing in robotics today. Obviously, when I started here at Northwestern in 2021, I didn't have to worry about ChatGPT. I wasn't thinking about the next humanoid startup. And since that very short amount of time, we have seen such progress in AI. We have seen such progress in what robots can do. And one of the big challenges that we're facing is that these robots need so much data to do the types of tasks that we envision them doing, in large part because the world is so incredibly unstructured, it's complex, it's dynamic. For building these simulation pipelines for deploying a robot, there's no way we're going to be able to simulate the whole world perfectly. And now we're asking this like very precise machine to figure out how do you do that? And that simulation requires this precise machine. And there's this whole disconnect between how we actually build robots and how we actually think about deploying them in a world we cannot control. And so that's the lesson of biology. Biology shows us that imprecision, imperfection is actually the key to being able to do the things we do in our environment. And one of the big lessons I hope we get to show robotics at some point is by getting away from mechanisms, by getting away from something so precise and rigid, by using things like artificial muscle-powered robots, we might be able to solve that challenge and not have to require so much data and actually get these robots in the real world doing things we need them to be doing.
I know I talked about that Disney character, Baymax. I mean, is that what we're talking about? This big Stay Puft marshmallow kind of soft inflatable robot?
I think that was a huge source of inspiration to get this field of soft robotics going. When we started thinking about Baymax as inspiration for robots, that was coming at a time where soft robotics was really coming into the discussion. Some of the original discussions around soft robotics were how can we make robots that are safe for people to interact with, or that are safe for people to be around. So if you go to any industrial robot, you're going to see caution tape everywhere. You're going to see these restricted areas because you're not sure if that robot's going to do something you don't want it to do, and it might hurt somebody, which is a real possibility. So the future of Baymax, of soft robots, really started with how can we make robots that are safer for people to be around. And in time, I think that's moved beyond just thinking about soft materials as being soft, but thinking about soft materials as being very productive and essential to performance, like we see with tissues like muscle, and enabling us to do the things that rigid robots can't. So in the last 10 years or so, there's been this really interesting kind of broadening, I would say, of the scope of what Baymax would have inspired. It's not just about a safe robot for us to be around, but where do new materials actually allow us to make robots that couldn't exist any other way?
One idea that runs through your work is that intelligence doesn't just live in the software, it can live in the body of the robot. When you say a robot's behavior can come from its materials, what does that really mean?
There are a number of conversations you could be a part of with faculty and program managers who are having us address this exact thing. So we know, for example, that the body can do things on its own without computation. Seth, I just saw on the camera, picked up a cup, and he wasn't solving some precise set of equations to pick that cup up. He's relying on his soft finger pads and tips to provide friction, to provide some sort of conformability around that object, to be able to pick it up and not have to think about the entire process. We know examples like that where the body can basically offload what the brain would otherwise need to do by using things like compliance and deformability. If you're running down a steep hill and you need to get some shock absorption to correct yourself, that is something a mechanism cannot do. Your body, your muscles, the tendons and ligaments joining your bones, all of those things work in concert to allow you to not have to compute every single operation your body does. And so that's where we mean by intelligence gets baked into the body or the materials. It's embodied in the structure and the mechanics of these materials, but we still have a long way to go to think about how to formalize these. And we design these material systems as we think about new actuators and sensors. As we put them into robots, we're getting to a point where we can now ask some really important questions about how does that body actually help intelligence? How does that body make a robot walk faster, for example? Or how might that robot start to use its body to do computations we otherwise don't have the reserves computationally or energetically for the robot to perform? So as we figure out how to make these materials do the things that we want these robots to do, as we actually formalize what we mean by the body embodies intelligence, these are the types of insights I think we need to overcome those limitations I've highlighted of rigid mechanical precise systems.
You brought up muscles quite a bit in this interview already, and you're spending a lot of time thinking about how to make stronger, more practical artificial muscles for robots. Why are muscles such a central piece of building robots that can take on human tasks?
That's a great question. I have been able to work with so many amazing people over my career, many collaborators, advisors. I give a guest lecture every year, and I open with a line from one of my former collaborators, Professor Robert Wood at Harvard. And he once said that muscle is the holy grail of all engineering. And that really stuck with me because I think he's right after all of these years. And if you look at muscle, it is this insanely amazing thing. You can find little muscle fibers in tardigrades all the way up to blue whales. Practically every swimming, walking animal has used muscle, and nature converged on this solution eons ago and has basically used it ever since. It is hard to think about any engineering technology that scales the length scales of a tardigrade to a blue whale. It is amazing what muscle can do, and it's amazing how many different length scales it actually assembles through in order to function. One of the reasons we're really excited about muscle is because it is so scalable. If we're talking about tardigrade legs to blue whale bodies, that signals that muscle is a really nice scalable actuator that we could imagine being distributed throughout a robot's body. That's in stark contrast to a little motor that might be driving a knee, and that's going to limit the different types of degrees of movement that are possible in a robot. One of the other nice features about muscle is it has a feature called backdrivability. What backdrivability essentially means is that robot can interact with the environment, and the environment can act back on the robot. That's a huge thing for us to think about in robotics because most motors don't allow for that. So if a motor's coming in and swinging you, that's why Baymax is useful. If a motor's coming in and swinging you, there's no backdrivability. It's going to keep knocking you over. You want a backdrivable muscle to basically sense you or not be able to hit you. And so backdrivability is how we interact with our environment really well. The environment kind of talks back to our body, and muscle does this incredibly well, in addition to that scalability. I think some other important things we could get into are just how muscle gets integrated into the body. You have a single motor unit firing a signal saying, go contract. We don't have that sort of single terminal input in a lot of our motors. It would be a great alleviator of so many systems design challenges if we could just have one little wire driving a little muscle. Muscle is not more efficient than the motors that we can make. However, when we think about all the muscle that we have, which for an average human male is about 50% of the body by weight, it would be hard to think about a system that is easier to power than a bunch of motors, which require these very, very heavy batteries. So I could go on and on of the different types of ways that we could use muscle and why it's so important. And it fundamentally stems from, I think muscle is like this holy grail of engineering. Certainly it's a holy grail of material science and engineering and being able to assemble all the way down to that nanoscale up to make something that would enable robots to literally behave, move, and do the things that animals can do.
So making soft materials perform like muscles isn't easy. Tell me, how's your lab approach this problem, and what have you learned from building artificial muscles that could actually power robotic systems?
Yeah, that's an amazing question. If you go back to muscle, biological muscle is all chemically powered. All of life is chemically powered. And we do not have good strategies for thinking about chemically powering a muscle yet. We approach this challenge from a couple of perspectives. We first really think about that material. How would it ultimately fold into a robot? I can use different types of inputs like light and heat. Are those going to be appropriate for a robot to be using? A lot of people have made some really wonderful advances in shape-changing materials, but we're constantly taking a kind of systems approach to think about how would we take those materials and actually get them into a robot that people could use. And the path to doing that is think about something that could be electrically driven, something that's going to be electrically powered, because that's where robotics is, and that's where it's going to be for quite some time. In our group, we try to think about different stimuli that we can trigger using electronic inputs, things that might be like electric fields or electric currents, or even things that are closely related like light, and trying to make light a more practical stimulus for these types of materials. I can talk about that set of projects, which basically is trying to figure out how can I use these inputs in a clever way to drive changes all the way down at the molecular scale to get these types of fibers. The other way that we do this is we think about, well, motors, those are really good still. Is there a way where we can motorize a material and still get a kind of artificial muscle-like behavior? And so some of the latest work from the group, especially led by a postdoc in our group named Dr. Tae-Kyung Kim and a very talented graduate student, Pranav Karthik, they have come up with ways of taking motors and basically rotating them and driving the shape of materials. We call these architected handed shearing auxetics, and they allow us to think now about how would we actually make different types of artificial muscles that we can electrically power and deploy in robots today.
You mentioned a little bit this idea of moving towards the nanoscale structures. How difficult is that, going from these larger muscle systems and then shrinking it down?
So we go the opposite direction. What we need to achieve molecularly, and then we expand that out. And so a lot of what we do as materials engineers is, okay, how is this actually going to be used in a robot? And then we know certain phenomena that we can trigger, control, and engineer at the nanomolecular scale. Now we have to make this gap, this leap, and that ties back to processing. We do a lot of work in our group thinking about materials that we can synthesize to port into these new processing methods that we develop. And we turn a lot in our group to additive manufacturing or 3D printing to create these materials. So for kind of these motorized materials we're using, that allows us to use desktop printers, which even high school students, junior high students could use. On the other side, we're using different types of extrusion processes to basically guide the ordering of nanomolecular scale features. And then because we're extruding, we can really scale these features up to something the size that's of relevance to roboticists. So we have a lot of work to do always in terms of not just getting this muscle, but then how do I make it practical? How do I make it cheap? How do I make it scalable? And that's where the engineering hat really has to be held on tight, because we've got to make sure that these materials actually can get manufactured and made into muscle people will care about.
I'd like to expand on that, how you think about scale and cost and manufacturability and how important that is, but also without killing kind of that creativity in the beginning phase when you're developing these systems.
As academics, right, we're caught in that exact kind of tension and trade-off. We have to think about things that are new and cutting edge and that are frontier opening kind of opportunities while still being checked by cost and practical use. I think especially with how quickly robotics is moving today, if you're not working on something that people could envision going into robot in 5 years, sometimes 2 or 10, like you probably are going to get dismissed as it's not going to be practical. So for us, we turn a lot to literature. We're not necessarily always trying to create new chemistries per se or completely new paradigms for how we do this, but taking that systems level perspective of I have to have something that's electrically drivable that could get into the hands of a roboticist already gives us a very clear direction on things that we should or shouldn't do. So I could create all sorts of really cool proposals around how I would actually try to make muscle, for example. And engineering biological muscle and trying to get that over to robot, it would just be a huge leap for us right now. It'd be a lot of work and not that near term, let's get this in a system today. We look a lot at old polymer papers. We look a lot with literature. What's great about being at Northwestern is how collaborative we are here. We get a lot of opportunities to engage across chemistry all the way to mechanical engineering. And so a lot of our collaborations really fuel the ways that we think about this. I will say that we're really trying to think about how to engineer existing kind of artificial muscle approaches rather than completely reinventing the new chemistries or the new paradigms. It's about trying to engineer what's already out there into a way that we can deploy into robots today.
In the future, you're thinking about whatever these could be in this 10, 20 years, these robots. What kind of task will they be taking on? How durable do you envision them being? And how could they change our lives?
That is the literal $1 trillion question, depending on who you are. Yeah, there's a number of directions. You're hearing me talk a lot about muscle. And I would say that as a materials engineering group, really addressing these challenges, it's components that really inspire what we work towards and less on the tasks. As a principal investigator, as a professor, I try to always create a lot of space for my students to come in with their own areas of what might inspire them, as opposed to me overlaying, hey, you should really care about this particular application. But for the projects that we're a part of right now, a lot of interest is in just achieving problems in dexterous manipulation. One of our big centers that we have the privilege of being part of is this engineering research center on human augmentation via dexterity. It's an NSF-funded ERC here led by Northwestern and colleagues at MIT, Carnegie Mellon, Texas A&M University, Florida A&M University. And we are, as a team, really trying to address some of these hardware level challenges to make dexterous hands. And by making dexterous hands, really trying to help augment people in terms of giving dexterous robots an opportunity to help support them in different manual tasks and things like assembly, manufacturing. The list goes kind of on and on. There's another set of programs and projects that we're working on that really focus more on locomotion. So manipulation is a really hard problem right now for robotics. That is that literal $1 trillion question. In terms of other opportunities, though, I'm still very much motivated by how do we get robots into the real world as quickly as possible, because that is a task that robots still cannot do today. So how can we make robot bodies that effectively allow robots to enter any environment? And if we can figure out that problem, not needing all this compute, not needing all this simulation time, then we get to help robots help us do really important things, whether that be cleaning up an oil spill or some natural disaster. If humans can't access something, could a robot instead? Could we think about like really horrible situations where we do not want people intervening? I can think of many where having a robot in the world do a task for us would just open up really important opportunities, but we cannot do that until we actually have robot bodies that are capable of resilient, adaptable behaviors.
I'm thinking of like during COVID-19 when doctors couldn't enter the rooms without a full body mask and gloves.
Healthcare through the roof, elder care through the roof right now. How do you make sure that you have the presence of a human, whether that be delivered in a teleoperation type sense or like literally having a robot assistant? We have a growing aging population and we don't have enough people coming to fill certain gaps to like serve in these roles. The natural disaster front is huge right now. We can't access certain areas when we have natural disasters. And so could you send a robot that can actually be prepared to walk through rubble that you can't simulate and rescue people or just notify? So industry right now is so focused on hands, quadrupeds, and humanoids, and it's very human benefit centric. And our hope, my hope, is that when we design these types of bodies, it will change the way we think about robots helping us. And especially with all the challenges that we face, we're going to need more help than I think humans alone can provide.
So I want to ask something that when I was reading about it, sounded pretty biological, and it's working on materials that move ions through a structure to create sensing. How does controlling ion movement across different scales give robots a new way of sensing the world?
Yeah, so you're touching on some things that are super frontier for us. And I would say like chapter 2 of this story. Muscle chapter's like hard enough. It's a whole deal. You're touching on a point though for us where it's like, once you have the muscle, how do you control this thing? And inevitably, what we know and are anticipating is if you start to change the body, if you start to change the hardware, you're probably going to have to change the whole control paradigm, how these robots learn. You have to reevaluate it. As we start to imagine what a future robot would look like, you might not rely on traditional computers. You might not rely on the pipelines that are already being developed right now because you have to create a totally new one. And when we look at biology, again, this is a chemically fueled machine, but everything in biology is ionically integrated. Those muscles that we care about, they're moving because of ion release into your muscle tissue. If you look at your brain, these are all transport of ions across many length scales. When you think about perception, that's a flow of ions being triggered. So the ion in biology is the electron we're currently using in robotics. And as material scientists and engineers thinking about multi-scale kind of material systems, we're increasingly interested in what opportunities start to open up. If you can take that same principle from biology of ionic transport as the thing that integrates all this together, can we start thinking now about certain types of sensors or even actuators as we've tried that can be driven or integrated through ionic phenomena?
How do you talk to the public about this and let them know the work that you're doing, how it may impact them someday, and understand what's out there right now in popular culture and what you're trying to do in your lab and what message you would like to let people know about this work?
Coming back to, we didn't have ChatGPT or humanoids when I started here. I did a postdoc at MIT's Computer Science and Artificial Intelligence lab. And I remember when I was interviewing for a fellowship to support that work, I got a lot of pushback on the idea of robots emerging as a robust technology because at that time it was a threat to jobs. And so if you're developing robots, are you taking a job away? And I think it's shocking to me to come to today, and that is there, but it's not this immediate wait, you're going to take jobs away. Instead, it's what can robots do that we do not have the labor force to deliver on. The way that this technology is changing too, obviously we can have a discussion on should you be using AI tools or should you not? And I think as these technologies emerge, it's going to take some time for us to think about how do we best utilize them. And I would never tell somebody to not utilize these AI tools. Figuring out how to augment your workflows with them, it's important. They're available and it can be helpful so long as you know how to responsibly use them. What we're trying to do is also think about how can we responsibly use these technologies. With the hand DRC, augmenting the human workforce, augmenting human capabilities with robotic capabilities, that in the right hands, that is not a scary thing. That is actually a really exciting thing and a huge opportunity, especially when you think about some of the healthcare benefits, some of the benefits to how we better take care of our planet. There's a huge number of reasons why these types of technologies, for me, bring a lot of hope. All technologies have their downsides. All technologies can be utilized poised for harm. I would say that a lot of what we're also trying to do is lower the cost of robots with the types of materials that we're making. And if we can lower costs, then we get to help democratize. We get to help bring access to these tools. So you're not looking at an Elon Musk humanoid that costs an enormous amount of money. Can we actually lower the cost of these systems, help them be more serviceable? And if you can do that, then that gets the opportunity for these to be technologies that can be accessible to more people. And that's another one of our big hopes in terms of how we address this challenge. If you look at time, there's many examples of making a technology more accessible typically correlates with a good thing for people. And so making robots that we can literally 3D print on a high schooler's printer is a huge opportunity that we see.
What would your ideal robot look like? Is it a humanoid, Tesla sleek thing?
What's happening in industry is really shifting a lot of people to think, oh, it has to be a humanoid, or are hands supposed to be human hands, or can hands be something completely different? Why does the next great humanoid have to have a hand that looks like a human's? There are some really exciting conversations going on right now of what robots should look like. And I think that kind of boils down to what do you envision this robot actually doing? When I think about the context of applications that are interesting and important to me, they do take more of like a quadrupedal type form. So think like a robot dog. Like those types of quadrupedal systems to me feel like they have the most opportunity. I don't want like a humanoid. That's not something necessarily that I envision as like my favorite. I've worked on tiny little octopus shaped soft robots. And once upon a time, I probably would have said an Octobot. But as we start to appreciate increasingly the importance of muscles and musculoskeletal systems and how these capabilities happen, and then you want to think about putting robots in the real world, things like dogs and dog-like robots that can move quickly or can also swim or traverse many different terrains. Those are the ones that I think that sit in my imagination. For full disclosure, we've written some proposals on a variety of different ones where organisms have come into the proposal. And I can say an iguana has shown up. One of my favorites was an otter showed up. Like an
Wow.
otter.
Cool.
And yeah, those are the two big ones I think that have come in, otter and iguana.
Vote for like a pointer dog or a doodle. Like, I think you have something there with the dog thing.
And just
Something,
for me, it's
something
like
hypoallergenic.
Yeah.
You know?
hypoallergenic for sure. When you think about like dog agility, or even like cheetahs are a huge, big source of inspiration too in a lot of these. Things that are agile, things that can move quickly. I would also say birds probably offer a lot of really cool opportunities that would have a different set of applications, but think like crows, really awesome. They have the ability to do really cool tool manipulation type skills. That would be a huge way to think about muscles doing things that like drones can, for example.
So I'm curious, we've touched on this a little bit, but how do you tell an artificial to move? And how do you measure whether it's good? Are there like metrics that you look at, like safety, lifetime, how much strain you can put on it?
I'll start by saying that robotics generally is not very good at measuring itself. And we have some papers in review right now that have taken a lot of work trying to back out key parameters, key metrics to do some comparison. Robotics does not like to reveal its performance capabilities for a number of reasons. I think as a field, we're also getting to a point where we need to compare. And so understanding how well a material behaves in a new field like soft robotics or in these bio-inspired domains, you do have to start to measure and deliver on some sort of metric or some sort of mark of success. For us, it always comes back to how are you going to actually use this in a robot? And so for us, things like power density. So how much power do I get basically packed in the weight of the actuator? It's a big one for us. It captures how much force I can output. It captures how much speed. Actuation bandwidth tends to be an important one in our community because a lot of these artificial muscle technologies are not very fast. And so for us, trying to figure out ways of improving that is a huge materials challenge. There are many ways I think that as the field of robotics moves and industry paves the way for us, the good part about all that is it is going to put pressure on us to do better in terms of characterizing and actually defining what sort of improvements we want to make. And I think that as we see many more developments in this space, it's going to help us on the academic side, those who are trying to make new types of materials, come up with well-defined metrics, because at the end of the day, we need to show the utility of these materials over things like conventional motors and actuators.
You did mention that your work is kind of starting at this molecular nano level and building up to this larger scale of what a robot could be. Can you talk about where you see the nanotechnology field going as far as its role in robotics and the future of robotics? robotics?
Yeah, so muscles are nanoscale machines working in concert to span, as we talked about, from tardigrades all the way up to blue whales. For us, we can't build those nanoscale machines. We don't have that capability, but we can focus on nanoscale domains within the materials that we care about and make sure that these domains actually get captured in the actual material that we're making. What do I mean by domains? I might mean just how a polymer organizes at the nanoscale. And the way that it organizes might allow me to use a stimulus like an electric field or light to move like I would want a muscle to do. And so understanding what chemistries and what processing methods allow me to achieve those nanostructures is eventually key to figuring out how to get these muscles to work in the first place. One of the big challenges, and this gets more into kind of materials engineering aspect, is, muscles using reservoirs of ions. We have these skeletal units. We have these motors crawling on the skeletal units. There's a lot going on. It's not one material, it's many materials working in aggregate. As we think about synthetic varieties, we have to think about dielectric materials, things that aren't going to conduct charge. We might want things that do conduct charge, that need to be really good electrodes. And we also have to be able to make metals soft and metals compliant. We have a lot of weird material trade-offs and conflicts that we're going to have to address. And nanoscale kind of considerations, nanomaterial engineering approaches will probably be absolutely essential to helping us figure out how to exactly create the materials we want with the exact mechanical or other properties that we want those materials to achieve. We have to think about all of that at the molecular scale, at the nanoscale, just to back out some of these capabilities. And especially as we envision ways of, say, miniaturizing these things even more than we currently are, that is the domain you're going to have to go in. If you actually want to approach something as thin as hair, you're going to have to go talk to somebody doing some sort of nanoscale assembly to even get to that part, because your muscles are thinner than that. There's a lot of huge opportunities for chemists and material scientists to join in this holy grail adventure of how do you make muscle.
Your work sits at this intersection of so many different fields. How do you train students to move across chemistry and bio and robotics and engineering? How do you keep them from feeling that they have to become experts in everything?
That's a great question. One of the things that I really strive to do is to not have students think that way, because you can't. As somebody who's working in an interdisciplinary space, your expertise is not being deep in each of those. Your expertise is deep at the intersection that you've just created. And so for my students, who are amazing, I have the best job because of the team that I get to be part of. We have chemists and deep chemistry background students in the group. We have deep robotics expertise students in the group. I think what the members of our team get to experience is they get to come in with a perspective. And so long as they broaden that perspective to include the full range, you're already ahead in terms of thinking about how you contextualize your emerging and growing expertise in this very big domain. I never will have a student, and I shouldn't have a student that can do everything, because they're not going to be able to do it all. In our group, it's evident that everybody develops their zone within this spectrum. And the strength of the team that we have built is that those all get to work together really well. The challenges ahead for robotics will get increasingly interdisciplinary. And the same way challenges ahead in materials are getting increasingly interdisciplinary. And as these fields blur more and more, we want to be right at that intersection already, saying, hey, we're already here first. Here's the insights, but also can continue to grow that community of saying, here's the new ways that we can contribute. Robotics is definitely something that we care a lot about. Not all my students actually care about robotics. They care about certain features of it or certain aspects that they can imagine being part of their own interest space. I think coming back to, I was a biomedical engineer by training and became a material scientist and studied robotics as a postdoc for a bit. For me, it's this whole adventure of trying to build weird bodies that actually have utility for robots is really a way to just kind of be humbled by what nature does. Biology is amazing. We talk about bio-inspired materials design all the time, but the system of life kind of gets to embody itself in robotics. And you just get this like really deep appreciation for biology makes this look so easy. And it is very difficult to try and replicate this. We have so much work to do, but I think the awe that you get from it and the humility that you get from it is really nice to have. And being able to translate this grand goal into other different areas is really fun to do with my students.
We keep hearing that. It's like science inspired by nature and how hard it is to replicate, but how inspiring it is and how many solutions can be found in nature and in human biology.
Yeah, it builds differently, it develops differently, it adapts differently. It's always going to beat us
quick on that point, do you see a difference? Because I've seen biomimicry and bioinspiration used almost interchangeably.
There's a huge difference. If I have these motorized materials, that is very much not biomimicry. It's inspiration to an extent of I'm trying to get something that is able to contract through the motors and the materials that we design. For some of the actual fiber-like actuators we're making, these more true kind of artificial muscles, we're again not capturing the exact mechanism of how muscle works. But we really rely on that understanding to translate how can we, with a broad brushstroke, get that to work in a material system? How can we get things to contract? How can we get things to be efficient? It's still bio-inspired heavily on that end too. If you really want to build bottom up, I want to build tiny little molecular motors up at some point, you're going to have to do something that's truly biomimetic, not just bio-inspired.
So, as we wrap up today, what's one thing that you want to leave listeners with as we think about the future of robotics and what we can expect in the next couple of decades?
If I could leave people with anything regarding robotics, the future is, I think, far more interesting than it might be scary and far more exciting. And I think the opportunities are going to show themselves as us really benefiting a lot from thinking about how to harness, use, partner, team up with autonomous systems. I think that thinking about how to make something that is more bio-inspired, something that's a little bit more lifelike, will only help facilitate that. And I hope people maintain a real sense of hope for what these types of capabilities can do and how they can help us live happier, healthier, better lives. That's certainly the vision that we see in this. It's not about negative things. It's not about things that are there to somehow take. If anything, it's about figuring out ways in which we can give new opportunities through these new capabilities.
Dr. Ryan Truby, this was a fantastic insight into your lab and all you're doing here.
I really appreciate it, and thank you guys for having me.
Thanks so much for listening. This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University. Be sure to follow this show on Apple Podcasts or wherever you listen to podcasts, and be sure to give us a 5-star review.
For more information about IIN, go to our website, iinano.org/podcast.